knows a lot about the science stuff. Professor Dave explains.
Say you walk into a crime scene. Maybe it's a trashed apartment, a stolen car ditched in an alley, or some creepy abandoned house straight out of a horror movie. You know the culprit touched something, a door handle, a glass, maybe even a body, but you can't see the fingerprints. That's the thing about fingerprints. They're always there, practically mocking you in their invisibility until you bring out the right tools. If criminals were kind enough to dip their fingers in paint before committing crimes, forensic work would be a breeze. But since they don't, science has to step in. Finding fingerprints isn't some magical ability, it's a process. And before you even think about powders, fuming, or chemicals, you need to answer one question. What kind of surface are we dealing with? The type of surface changes everything. Fingerprints don't behave the same way on glass as they do on paper, just like spilling coffee on a napkin doesn't look the same as spilling it on a table. That's why forensic experts divide surfaces into two main types, porous and non-porous. Porous surfaces are the real troublemakers. Paper, cardboard, fabric, untreated wood, these soak up fingerprint residue like a sponge. The oils, sweat, and amino acids left behind by a fingertip don't just sit on top, they seep in, becoming part of the material itself. That means regular powder won't work here. Instead, we need chemical reactions to make the prints appear. More on that in a moment. Non-porous surfaces, on the other hand, are the easy ones. Smooth surfaces like glass, plastic, polished metal, and ceramic don't absorb fingerprint residue. Everything just sits there waiting to be found. Powders work well here, and if we want something more permanent, chemical fuming seals the deal. And then we have the wild cards, the semi-porous surfaces, such as leather, wax paper, and certain painted surfaces. They don't fully absorb prints, but they don't keep them sitting on top either. These are unpredictable, and getting prints off them might require a combination of different techniques. Alright, so we've got our surfaces figured out. Now let's actually make these fingerprints show up. The first thing crime scene investigators try isn't powder or chemicals, it's light. Alternate light sources, or ALS, use UV, infrared, or laser-based lights to scan surfaces for hidden prints. Some substances in fingerprints, like sweat, oil, and salt, glow under certain wavelengths. If a fingerprint lights up under UV, that's great. No need for chemicals and no risk of damaging evidence. But if nothing shows up, it's time to bring in the real tools. For non-porous surfaces, fingerprint powders are the easiest and most common method. The principle here is adhesion. The fine particles in the powder stick to the sweat and oils left behind by the fingerprint ridges. The better the ridges, the better the adhesion, making the print visible. Black powder is the way to go. It's made of carbon or charcoal and stands out well on light-colored surfaces. Similarly, for a dark-colored surface, a light-colored powder is used for enhancing the contrast. If we're dealing with something delicate, though, magnetic powder is the way to go. Instead of using a brush, forensic experts apply it with a magnetic wand, reducing the risk of smudging, and for those annoying multicolored or patterned surfaces, fluorescent powder saves the day. It glows under UV light, making the fingerprint pop even when the background is distracting. But sometimes powders just aren't enough. Maybe the print is too faint, or we need to preserve it for longer. That's where superglue fuming, such as cyanoacrylate fuming, comes in. This works on the simple principle of polymerization. When heated, the fumes from superglue react with fingerprint residue and form a hard white polymer coating over the ridges. The print is now locked in place, meaning it won't smudge or fade easily. Since this method works great on non-porous surfaces like glass, plastic, and metal, it's a favorite for crime scene investigators handling objects that might be moved around or exposed to the elements. The developed fingerprint impressions are lifted, using tape at the end and subsequently photographed. Now, what if we're dealing with a porous surface? Powders are useless here because the print is already inside the material. We need chemicals that react with fingerprint components and drag them into visibility. Ninhydrin is the best candidate for this job. Originally used for qualitative analysis of proteins, ninhydrin reacts with amino acids in sweat, turning prints into a lovely shade of purple-blue, called Ruhrmann's purple, named after the scientist who discovered ninhydrin. The reaction takes a while, but a little heat speeds things up. If you've ever seen forensic scientists proudly holding up a piece of paper with a bunch of purple fingerprints on it, that's ninhydrin doing its job. For something even more sensitive, there's DFO, or 1,8-diazofluoran-9-one. This also reacts with amino acids, but with an interesting twist. It fluoresces under UV light. That makes it easier to spot faint prints and capture them clearly. More contrast means better visibility. And then we have silver nitrate, the last resort. This works by a different principle, precipitation. It reacts with sodium chloride salt in sweat, forming silver chloride. When exposed to light, silver chloride darkens, revealing the fingerprint. The catch is that silver nitrate permanently alters the fingerprint residue, meaning there's no second chance. If you mess up the exposure, the print is gone forever. That's why this technique is a last resort. There's one other method that can be considered as fitting under both physical and chemical categories. It works through sublimation, like iodine fuming. Iodine crystals, when heated, turn straight into gas. These gas vapors then adsorb on the fingerprint residue, temporarily revealing prints in a brownish shade. The downside is that the prints fade fast. If you don't fix them with a starch solution or benzoflavone or snap a quick photo, they're gone. Because this involves fixation through a chemical reaction with iodine, it can also be regarded as a chemical approach. Though less popular nowadays, it is held in high regard due to its simplicity and cost-effectiveness. Fingerprint detection isn't just about randomly picking a method and hoping for the best. It's about understanding the science behind it, whether it's adhesion, polymerization, amino acid reactions, or salt precipitation. Everything depends on the surface. Smooth, non-porous surface, powders and superglue fuming. Porous surface, ninhydrin and DFO. A standard protocol involving sequential processing is conducted in fingerprint development, in which the least invasive method is done first, followed by the more invasive methods. Remember, the fingerprint is not the sole evidence out there. The object on which the fingerprint is deposited is itself a piece of evidence. Sequential processing ensures that the substrates are not destroyed. Reversibility, substrate sensitivity, and risk of overdevelopment are the three main pillars of sequential processing. Let's consider alternative light sources, iodine fuming, and ninhydrin. What should be the correct order? The first should be obvious, ALS, which is non-invasive. Second, iodine fuming, as it is a reversible reaction, given that it fades. Last would be ninhydrin, because it permanently alters the fingerprint. There are even stranger techniques out there, such as vacuum metal deposition, specialized chemical treatments, and methods that can recover fingerprints from materials you'd never expect. However, whatever the development method is, it ends up in photography, followed by enhancement of the photographs to visualize as many ridge characteristics from the image as possible. For now, just take a look at the objects around you. Every table, phone, and water bottle is covered in your fingerprints. Try to use a paintbrush and see if you can develop a fingerprint on your phone screen by using talcum powder. Then lift it using tape, capture a photo, and try playing with image enhancement to study the ridge characteristics. Then let's move on and learn about fingerprint development.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.